I'd like to take this time to thank everyone for joining in today for CCJ's first webinar of the year. My name is Scott Schwieger. I'm the editor of Combined Cycle Journal, and you probably know me from lots of webinars and virtual conferences over the past few years. So I'd like to kick it off now. Our topic today is eliminating varnish-related failures through lubricant chemistry management. Our presenter is Matthew Hobbs of EPT Clean Oil. He's the Manager of Technical Services, Research and Development. Matt has a Ph.D. in synthetic chemistry from the University of Calgary. He's got a lot to share. He's got a lot of knowledge, and you're in for a real treat today. So without further ado, I'd like to pass it over to Matt.
All right. Thank you very much, Scott. Thanks for the intro. Thanks for the opportunity to present today. And yeah, thank you to everyone who's joining us today to spend an hour of your time with myself, with Scott, with CCJ here. Saw the registration list, and we have people from all different time zones. So thank you very much for making the time for this wherever in the world you are. All right, so we're presenting online today. We got people all around the world. I thought I'd just start, before we dive right into the lubricant chemistry management, by sharing a bit about where I'm presenting from today. EPT Clean Oil is based in Calgary, Alberta, Canada. That's home for me as well, and about 1.3 million other Canadians. And for anyone who's not familiar with their Canadian geography, we're in Western Canada, just on the edge of the beautiful Canadian Rocky Mountains. You can see those nice snow-capped peaks make for a nice background. They're about an hour's drive away from the city. So it makes Calgary a great place to live, to work, to visit, if you like getting out to the mountains like I do. Now, apart from being located close to the Rocky Mountains, what else can I tell you about EPT Clean Oil? Well, today's webinar topic is really near and dear to our hearts. Lubricant chemistry management really is at the foundation of everything we do. At EPT Clean Oil, we've made it our mission to teach the world a better way when it comes to maintaining their critical industrial oils. And we believe that that better way is lubricant chemistry management. Now, we'll talk about it a fair bit throughout the presentation, but just wanted to introduce it quickly here. When I talk about lubricant chemistry management, I'm talking about a two-pillar approach to managing our oils. The first pillar involves oil analysis, expert condition monitoring, because you are blind to your lubricant's chemistry if you are not running a good oil analysis program. And the second pillar of lubricant chemistry management is actually addressing problems with lubricant chemistry. So using filtration techniques, fluid conditioning, and in particular at EPT Clean Oil, we are big advocates for the use of ion exchange resins, using our ICB ion exchange resins to treat lubricants and to manage their chemistry. Now, we've been doing this for over 30 years, and over the course of that time, we've been able to install our products and to help end users at thousands of different sites. Now, we're also active in terms of getting our message out there. I mean, this is the reason that we do webinars like the one we're doing today, the reason that we are active on the ASTM's Turbine Oil Committee, on the STLE's Power Gen Committee, and with ICML when it relates to the development of their varnish content as well. Because again, our mission is to teach the world a better way. So what is that better way? Well, this slide really outlines, the path forward, the best way that we can be doing things here in terms of lubricant chemistry management. And usually this slide is something we build up to. Usually this is something that I stick at the end of the presentation and we build up to it. But for the purpose of today's webinar, I thought it would be fun to kind of put it up front to give everyone that sneak peek of where we're going and why this is so important. So this better way of doing things, in this instance, involves a case study. So this was a pipeline operator, and as a pipeline operator, they had a series of compressor stations, basically across North America, 80 turbo compressors operating in those stations. And the data on this slide comes from a peer-reviewed ASTM study that looks at the benefit that this end user got out of managing their lubricant chemistry much more effectively by using ICB ion exchange resins. They made the decision to do so a long time ago, over 37 years ago, and they're still going on this. So the ASTM paper that's shown on the right of the slide here, it outlines basically the benefits that they got out of this improved maintenance regime. They were able to save nearly $100 million in terms of their maintenance costs. And more important than the dollars and cents, perhaps, in today's environment, is the sustainability related benefit that they saw out of this as well. By more effectively managing their lubricant chemistry, they were able to dramatically extend the lifetime of their fluids. And as a result, that prevented about 15 million kilograms of CO2 from being emitted. So this is the better way of doing things. But unfortunately, not everyone is there right now. In fact, many people, many end users are not there at the moment. So in order to understand how we can get people that way, I find it useful to take a bit of a step back here and to look at what we are doing right now. We've got to understand where we're at in order to plot the course forward to where we want to go. So examining current oil maintenance practices, Well, essentially the current approach to oil maintenance, it's outdated. It tends to be reactive in scope. And I would argue that it is as outdated as the payphone, which is shown on the slide on the right here. Currently, we spend the bulk of our efforts when it comes to oil maintenance, removing dirt and removing water. And it's really, really important to keep our oils clean and dry. But one thing that we've always found very interesting at EPT Clean Oil is that, we're applying so much of our maintenance efforts and budget towards removing particles and water, but those aren't the basis upon which oils are condemned. Bit of a spoiler alert here, but oils are condemned on the basis of their chemical breakdown, which results in varnish formation. Obviously, we'll be talking about that a lot later. Getting back to the current approach, oil analysis is recognized as being a very useful maintenance tool in many oil maintenance programs. Unfortunately, we see a lot of end users that are running oil analysis and they are missing key tests. And as a result of not running all of the right tests, perhaps the right way or perhaps at the right frequency, their oil life is not well understood and it is not well managed at present. And as a result, their programs aren't really sustainable. The oil is treated much like a consumable, much like the oil that we have in our car engines. You use the oil degrades chemically, and once it is degraded past point X, you throw it out. This isn't a sustainable approach. It's one thing to do this with the relatively small oil volumes that are present in our car engines. But if you're operating a 20,000 liter or 5,000 gallon turbine oil system, obviously it's not sustainable to just treat that oil like a consumable. All right, so a bit of a case study showing business as usual. This is an oil and gas facility. They're operating a 9E gas turbine. And like so many others out there, their maintenance is reactive in scope. They're not really doing anything when it comes to managing their lubricant chemistry. As a result, their oil degrades while it is in service, and typically a gas turbine oil may last for only 2 to 5 years. And once it is degraded beyond point X once again, it's simply replaced. So as a result of the failure to manage this lubricant's chemistry, well, number one, this person's or this user's turbine oil was often in suboptimal condition. Because it's in good condition in terms of its chemistry when it's installed, but after a year or two of service, that oil has started to break down and its condition is now suboptimal. And as a result of that suboptimal condition, this end user reported 24 hours of unplanned downtime per year. So you do some math here, and in terms of the losses that results in at this plant, the production loss amounted to nearly $370,000 annually. So that's a pretty significant cost associated with doing business as usual and being reactive. And that's just the cost of lost production. That's not the cost of actually repairing the turbine, getting it back up and running. You multiply out that annual loss over the 25-year lifespan of the asset, that's about a $9.2 million avoidable loss. And I say avoidable because if you manage lubricant chemistry, you can avoid losses like this. So this business as usual approach obviously isn't good enough, and that presents us with an opportunity. And that opportunity is to close critical gaps with lubricant chemistry management. And as we shall see, when you do this, this allows you to operate more reliably, more profitably, and more sustainably. So again, what do I mean when I say lubricant chemistry management? Well, I'm talking about this two-pillar approach. The first pillar is oil analysis. You've got to run the right tests the right way. You got to make sure you're doing so with the right frequency. And when you get the results back, you need to act on those results. And in doing so, you're going to generate the data that is required to more effectively manage your lubricant's life cycle. Once you have those oil analysis reports in hand, again, you have to act on things. You have to apply your maintenance budget towards the actual cause of failures. It's absolutely imperative that we keep our oils clean and dry. But again, if we're condemning those oils and experiencing oil-related failures on the basis of lubricant chemistry, we need to take steps to manage that chemistry. So we're going to talk about each of these two pillars in more detail in the following sections here. So pillar one, oil analysis. This is a section I like to call "You can't manage what you're blind to," because again, oil analysis really is your window into your lubricant's chemistry. So oil analysis has long been recognized as a key part of maintenance programs. Now, despite the importance of oil analysis to your overall maintenance program, we find that many end users are entirely reliant almost on third-party labs to do their oil analysis. They rely on third-party labs to tell them what test package they should be running. The third-party labs test the samples for them, and then often the third-party labs have, some sort of computer algorithm that generates reports, and end users often rely on this to interpret the results as well. They rely on the computer algorithm to highlight things that are off spec, that are not the way they should be. Now, in order to get true value out of an oil analysis program, it's one thing to outsource the testing. We completely understand that, not everyone has the resources or in terms of staff, in terms of expertise to set up an oil analysis lab on site. So it's one thing to outsource the tests, but you really have to understand the testing that you are doing in order to get real value out of the results. And again, if you don't understand the results that you're getting back, then it's going to be very difficult to act on those. So to help people understand their oil analysis reports, I always suggest that people kind of sit down and they ask some key questions when they get a report back. And essentially these questions are kind of a way of triaging your oil analysis. You deal, with the most important issues, the ones that are most likely to cause a failure imminently up front, and you work your way down the list. Now, because something's at the bottom of the list doesn't mean it's unimportant. It just means that it's a problem that might be, felt tomorrow, not today. So the very first question I always advocate that people ask when they look at their oil analysis report is, will this oil still do its job? And to answer that question, the single most important property that you can look at is the oil's viscosity. Because, if the oil is too thick, you have reduced efficiency, increased friction, heat can start building up, and basically, as the oil gets too thick, it's not an effective lubricant anymore. Oil being too thin, well, that's even worse still because, for instance, in a turbine application where you've got journal bearings, too thin of an oil, and you could have the possibility of metal on metal contact, and obviously that's a worst case scenario. So viscosity is really paramount to will your oil still do its job. Next down the list, could my equipment fail imminently? We've talked about particles in water and the importance of keeping your oil clean and dry. Taking a look at metals levels also gives you some insight into failures which may be in progress. So this is what you need to look at next. Look at contamination levels. And fortunately, these are relatively easy to solve if you see issues. You can improve your filtration. You can change the filters on site, or you can bring in a kidney loop filter skid to remove particles. Water, you can use a dry air blanket, dry gas blanket, dry nitrogen blanket, vacuum dehydration, centrifuge, potentially all sorts of things available, tools available to you to keep these contaminants out of the oil. The third and final question is the one that we're going to focus on the most here, because I feel like this is the question where people, or the area where people and oil analysis labs are falling down, where current maintenance programs are falling down. Is my oil chemistry failing? And again, this question is often neglected because we tend to look at the turbine as the asset and the oil as the consumable. But if you start to think about the oil as a consumable, you've got to be concerned about whether its chemistry is failing. And to answer that question, you look at oil breakdown levels. So specifically, we're going to hone in on varnish because it causes a lot of problems, but it's also important to look at varnish precursors like acids and oxidation products. Now, typically, we see third-party lab reports. They do a really good job of addressing bullet points 1 and 2 here. But we see issues with this is my oil chemistry failing. I mean, everyone's lab reports acid number, but all too often I see turbine or compressor users who don't have an MPC varnish potential test on their oil analysis report. This is a test that they will do maybe once a year to make sure they're in the good still. But as we shall see on the slides that follow, this is a test that you should be running much more frequently than that, in my opinion. Okay, so let's look at that question. Is my oil chemistry failing? Recall that oils are condemned on the basis of chemical breakdown. And one of the reasons that they are condemned on the basis of chemical breakdown is that that chemical breakdown leads to the formation of varnish. And varnish, as it turns out, is the most common cause of oil-related downtime in gas turbine applications. So in gas turbines, we always talk about varnish leading to valve sticking and subsequent unit trips, which are problematic. But the problems that varnish causes are not limited to unit trips in gas turbines. Basically, in any lubricant system, varnish can lead to a variety of other issues in addition to valve sticking. Things like filter plugging, things like high temperature operation, equipment wear, and poor heater and cooler performance. And again, one of the big issues that we see over and over again is end users not routinely testing their oil for its varnish content or varnish potential. So you don't want to be blind to your oil's chemistry. I mean, if varnish is the most common cause of unplanned downtime in a gas turbine application, that's a test you should be running more than once a year. So if you want to see your oil's chemistry, you want to see the varnish that might be there, you have to run the right test. And the right test is MPC, membrane patch colorimetry. And the test method is outlined in ASTM D7843. So on the surface, this test is a relatively simple one. The oil sample is passed through a 0.45 micron lab filter patch, and it leaves behind a stain if there is varnish present in the oil. So you can see some example patches on the right of the slide. A fluid that had very little varnish potential, it tends to leave no stain on the patch. So the patch looks white, and you see that on the left. As the varnish potential of a fluid increases, there are more oil breakdown products present in that fluid, and you're going to get a darker, more intense stain captured on the filter patch. You quantify the color of that stain, the intensity of that color, as MPC delta E, and this is what is reported by the test method. And basically, if you have a dark patch, that's going to be a high delta E value. That means your fluid had a high varnish potential. Now that's the right test, but it's also equally important to make sure that your lab is running that right test the right way. So again, on the surface, this MPC test is a relatively simple patch test, but when you actually look up the D7843 test method, you'll see that there are some key sample prep steps that are necessary to obtain consistent and reliable data from your lab. So namely, upon receipt in the lab, that oil sample has to be heated for 24 hours to 60 degrees Celsius, and then it needs to be incubated at room temperature in the dark for 72 hours. Why are these steps important? Well, varnish, as we will see on some of the slides that follow, is a shapeshifter. It exists in a soluble or dissolved state, and it can crash out as an insoluble state as well. So as your oil sample, after your oil sample has been taken, as it gets shipped to the lab, some of the varnish that was dissolved at operating temperature and under operating conditions may start to precipitate from the fluid, become insoluble. So when the labs get these, we need to reset them. And we do this by heating them up. That redissolves the varnish. It allows some of that varnish to become dissolved or soluble again. You then incubate it at room temperature for 72 hours so that every oil sample that's tested in every lab around the world has this 72-hour period. It is consistent for varnish to begin to crash out and become insoluble. Because what we're doing at the end of the day here with the MPC test is a patch test. We are capturing insolubles, things that are greater than 0.45 microns in size, on this filter patch. So they need to be insoluble in order to be captured. So it's very important that each lab is doing this consistently If you're not holding the sample for 72 hours, for a shorter time, for instance, not as much varnish may come out of solution. You may see a lighter patch. If you do longer time periods, you go 5 days instead of 3 days, for instance, you may see darker stains on the patch as you allow more varnish to crash out of solution. So that we're always comparing apples to apples between every lab on the planet and every test that each individual lab runs, it's really important to be consistent with this 72-hour hold time. It's so important, in fact, that ASTM D7843 actually requires oil analysis labs not just to report the delta E value of the MPC test, but also to report that 72-hour hold time. And again, this is an issue that we see over and over again with oil analysis reports. We very frequently see oil analysis reports from third-party labs that report the delta E but do not report the 72-hour hold time. So this is a little bit of an exercise that I always encourage people to go back and take a look at your lab reports after the webinars over here. Check and see if your lab's reporting that 72-hour hold time, because if they are not compliant with the D7843 method. And I would reach out and get in touch with them about that. Make absolutely sure that they are doing the right test the right way, because you're using the data that you get back from this test to make important maintenance decisions. So you need to be confident in that data. Okay, so why is this 72-hour hold time so important again? Why would I care about varnish that, was dissolved in the oil sample? Well, as I alluded to a few slides ago, varnish is a shapeshifter. So just because varnish is dissolved under one set of conditions or in one region of a system, that doesn't mean that it will stay dissolved or soluble elsewhere. It can cause problems throughout the system, even if it is, dissolved at the bearing, for instance, it can crash out in a cooler. And the reason that this can happen is that an oil's ability to hold varnish, to keep it dissolved in solution, it is temperature dependent. We refer to this as saturation. Basically, when an oil is holding all of the varnish that it can and keeping that varnish dissolved, it is saturated. But any additional varnish that is present beyond that saturation point will lead to the formation of insoluble varnish. And we have a video here that I like to use just to demonstrate this. We've got 2 beakers of the exact same in-service turbine oil. The beaker on the left is as received, out of the equipment, and it is saturated with varnish. The beaker on the right, we've removed the varnish from this using ICB ion exchange resins. Now, at a relatively warm temperature, 50 C or 120 F, operating temperature for instance, we see that both of these fluids look the same because soluble varnish, well, it's not visible to the naked eye. Both of the oils are relatively clear, they're both relatively bright, they're transparent. You can see the thermometer through them is the thing I like to point out. Now let's watch what happens as the oils cool. As the oils cool, their ability to keep soluble varnish dissolved is inherently less. And you can see the beaker on the left where there was some dissolved varnish start to become hazy, and eventually it becomes altogether opaque and you can no longer see the thermometer through that oil sample. So what's happening here? Well, the varnish that was dissolved in that fluid at a warmer temperature, as the oil cools, it crashes out as a fine varnish particle, and these fine varnish particles actually scatter light so that you can no longer see through this beaker. The beaker on the right, by contrast, well, there was no soluble varnish in it, so there was nothing to form insoluble varnish from as the oil cooled. And this really highlights the importance of making sure that you're running the right test, the MPC test, and the right way, the 72-hour hold time, to make sure that you see both soluble and insoluble varnish in your result. Because you need to detect both forms of varnish. It's not one form or the other that is specifically responsible for problems. They can both lead to problems. So this starts to segue over towards pillar 2 of lubricant chemistry management, and this is actually doing something about the problem, not just seeing the problem and being aware of it, actually managing it. So when it comes to varnish management, again, a bit of a refresher. Varnish is the most common cause of oil-related downtime in a gas turbine application, and it causes problems in a variety of other applications as well. At the end of the day, chemical breakdown, which leads to varnish formation, this is the reason that oils are condemned. Now, historically, again, we've looked at oils as consumables, and we've looked at this breakdown process as something that is unavoidable. You just have to change the oil once it's degraded. But that is not the case. Varnish formation and oil breakdown in general they are the end result of unmanaged oil breakdown, unmanaged lubricant chemistry. So this is something we can avoid if we manage lubricant chemistry. If we do this, we can prevent the formation of both soluble and insoluble varnish, and in doing so, we can eliminate varnish-related losses. And again, that was the title of today's presentation. The whole point of this is to prevent varnish problems. Okay, so segueing over to pillar 2, managing the unmanaged, lubricant chemistry management, that aspect of our maintenance programs that, we've hitherto often not been doing. When it comes to managing varnish, there are a variety of different products, different solutions available on the market right now. Now, regardless of the brand name or the company flag that any of these solutions are flying, they will operate based on one of 3 strategies, one of 3 principles. So the first strategy involves attempting to redissolve varnish, to take varnish which is insoluble and to redissolve it, to put it back into its soluble state. And we can use a variety of different chemical additives to do this, things like cleaners or solvency enhancers, solubilizers. Another strategy for dealing with varnish, and the one that we see most often, is particle removal systems. So conventional sieve-type filtration. So this could be electrostatic filtration, this could be, depth filtration. Essentially, at the end of the day, these are all technologies that remove insoluble species from a fluid as a function of their size. They will remove things that are 3 microns and up, for instance, or 1 micron and up. The third and final strategy, and the one that we are the biggest advocates for at EPT Clean Oil, is the use of ion exchange resins. And specifically, we believe that our ICB resins are the best suited to this task. So let's examine each of these strategies just in a little bit more detail and see what their strengths are and where they fail as well. So that first strategy, using some sort of solvency enhancing additive or cleaner, well, that might get the varnish that is plated off your equipment surfaces, but the underlying issue is that these additives, they don't remove varnish, they just suspend it or dissolve it within solution. And as we saw previously, varnish is a shapeshifter. Just because it is dissolved does not mean it is gone, does not mean it cannot cause problems. So these sort of additives can potentially be useful on a short-term basis, but they do not provide a long-term solution because they do not actually address the root cause of varnish problems, which is soluble varnish and other soluble oil breakdown products. That soluble varnish can still cause problems elsewhere in the system. It can still lead to issues if the oil cools, if conditions change, or if more oil breakdown takes place and the oil becomes saturated again. The next strategy, particle removal systems. Again, these are a very useful tool because it's absolutely imperative that you keep your oil clean. But these only remove insoluble varnish. Soluble varnish is dissolved. It will pass right through any sieve-type filter. I mean, using one of these to remove varnish is akin to trying to remove the sugar from your coffee using a coffee filter. It will not happen. That sugar is dissolved. It goes straight through the filter, much like soluble varnish goes through conventional filters. And that soluble varnish, if you're leaving it behind, it's a shapeshifter. It can still cause problems elsewhere. So this brings us to the third strategy, ion exchange resins and soluble varnish removal in general. We believe this is the better way to manage lubricant chemistry, and we believe that our ICB ion exchange resins are the best product available to do this. These ICB resins are engineered products, and they have been engineered to selectively remove varnish and other oil breakdown products. We do this by tuning the chemistry on the resin bead and tuning the bead's physical properties as well, so that they are optimized to remove soluble varnish and to do so selectively. Essentially, the oil breakdown products that are responsible for varnish problems, these become more attracted to the resin surface than they do to mechanical surfaces within your system. So you can use this to directly remove species that are actually dissolved. And when you do that, you also interrupt the varnish formation cycle at its earliest possible stage. As soon as that oil undergoes any form of breakdown, really, you're pulling out that breakdown product before it has a chance to go forward and to start generating soluble and insoluble varnish and even more damaging varnish deposits. So this is much more proactive or preventative, certainly, in terms of a maintenance strategy than the other two, which are reactive. They wait for varnish to be a problem before addressing it. Now, quite fortunately, ion exchange resins like ICB, they don't just remove soluble varnish. I mean, it's wonderful to prevent varnish formation, but if you already have a system that has varnish in it and there's already varnish coated out on your components, you're going to want to address that as well. Well, it turns out that when you remove soluble varnish, that also impacts previously deposited insoluble varnish, varnish deposits, etc. And the reason that this happened, like I stated a little earlier on in the presentation, is that every oil has some inherent ability to keep varnish dissolved, to keep it in solution. When when an oil is holding all the varnish that it can, that oil is saturated. Well, if you remove the soluble varnish, the dissolved varnish from that oil, you're restoring that oil to an unsaturated state. And that means that that oil has some finite capacity to dissolve varnish, which is no longer being used. And if there is insoluble varnish present in a system, some of that insoluble varnish will then redissolve into the oil. Essentially, this allows the oil to clean your system for you. Now, once that insoluble varnish is redissolved and is soluble once more, ion exchange resins can remove it. And by removing it again, we're cleaning the oil again, allowing the oil to clean the system. We have a sort of positive feedback loop that can drive the complete cleanup of both soluble and insoluble varnish from a system. And again, we've got a nice little animation here just to make this clear for everyone. So for the purposes of this animation, soluble varnish is being shown as a black speck, a black particle in the oil. Of course, soluble varnish is actually dissolved. It's actually invisible. You can't see it, but you got to show it somehow. So we're going to play this, and you can see that as this oil is put into service, it darkens, it degrades. There's more and more soluble varnish in it, and that starts to plate out on this servo valve spool, causing a varnish deposit. When you use an ion exchange resin, you can remove the soluble varnish. The oil is no longer saturated. It has some ability to hold varnish in solution now, and you see the varnish deposits starting to come off the equipment's surface. And of course, as they come off the equipment's surface, they are dissolved now, and they can be removed by the ion exchange resin. So you're cleaning up both the spool and the oil in this example. And the animation's really nice. It's some great work by our marketing team at EPT Clean Oil, but the proof is really in the pudding. Sometimes a picture is worth 1,000 words. This is a case study, Siemens SGT 800 turbine. Before and after they installed a soluble varnish removal system, which uses ICB ion exchange resin. You can see before there was varnish coated out all over these gear surfaces. At the next outage, for instance, when they opened things up to have a look after they had installed a soluble varnish removal system, you can see that those surfaces are clean. The varnish has been removed. Okay, so it's at this point in the presentation, we've now seen the two pillars of lubricant chemistry management: oil analysis so that you can see your lubricant's chemistry, and lubricant conditioning, varnish removal, so that you can actually manage it. I now want to tie this in and show you how this brings us to that better way slide that we had at the very start of the presentation. Because again, it's our mission at EPT Clean Oil to show the world a better way of managing their lubricants. So I'm going to talk about sustainability because that's a big topic, and that's a big reason why we believe that lubricant chemistry management is the better way. Sustainability is a 21st century operational tenet. When I first put this slide down onto paper, for lack of better terms, onto PowerPoint, I guess, I had written environmental tenet here, but really sustainability is much more than that. It needs to touch on all aspects of our operations. Now, despite the importance of sustainability, I acknowledge that this term is used very, very often. It is a buzzword, and as a result, it sometimes loses some of its meaning. So I thought it would be a useful exercise here to put the definition of sustainability on the slide so that, instead of thinking this is a buzzword, we can take a fresh set of eyes and look at it as, in this instance, the Collins Dictionary defines it. Sustainability is defined as the ability to be maintained at a steady level without exhausting natural resources or causing severe ecological damage. Now, the thing that I like most about that definition of sustainability is it shows a very clear link between sustainability and maintenance. So if we want to operate more sustainably, as we must, then one of the things we can do is we can follow best practices for oil maintenance. And again, we believe that the best and the better way of doing that is lubricant chemistry management. So why is this a problem? Well, emissions are the big problem here, because when we're talking about the end users of critical industrial equipment, we're often talking about the energy sector or power gen. And we know that current CO2 emissions are not sustainable. This is the reason that nations and corporations around the world have made commitments to reduce their emissions. When you look up greenhouse gas emissions globally, the energy sector accounts for a whopping 76% of them. And of those, power gen is responsible for about 1/3. To see just how big an issue this is in the energy sector and in power gen, have some fun with this. Just Google pollution. If you do a Google image search of pollution, about 95% of the images that show up are smokestacks from a power plant. So this is a good news, bad news situation. No one really wants to be associated with that, Wikipedia image that comes from the Wikipedia article for pollution on the right of the slide. No one wants to be associated with that. But the good news out of this is that because power gen and the energy sector are responsible for so much of the emissions in the world today, it means that small changes have the opportunity in these industries to make a big impact. And again, this takes on increased importance in light of recent commitments to net zero 2050. If any of us are going to get there, it's going to take a number of large changes and a number of small changes as well. And one of the changes that we would advocate for, again, is better, more sustainable oil management, because this will allow us to reduce our impact. And lubricant chemistry management is the way that we would advocate for doing this. So at this point, I kind of like to have a little bit of fun with things. When it comes to environmentalism, we're all very familiar with the 3 R's. Anyone that was in grade school in the 70s, 80s, or 90s will have had these drilled into them in terms of waste management. We want to reduce, we want to reuse, we want to recycle. And we're a lot further ahead with respect to all of these than we were in the 70s, 80s, and 90s. But I thought it might be a little bit of fun to do the 3 R's of lubricant chemistry management, because they highlight how this process works, why it's important, and how it ties into sustainability. So when it comes to the 3 R's of lubricant chemistry management, these are rethink, remove, and restore. So let's talk about rethink first, because it is the biggest one. We will spend the most time discussing rethink, because it's really about rethinking business as usual. We can't keep doing the same thing the same way. We have to rethink things. In terms of our assets, it's time to rethink these. It's not just about the machine. It's not just about the turbine or the compressor. Historically, we've looked at that as the asset, excuse me, and at the oil as a consumable. But the oils, as it turns out, are assets too. It's just that our current approach to maintenance is not treating them as such. Now, to convince yourself that an oil is an asset, just take a look at the things that happen when we do poor oil maintenance. Poor oil maintenance leads to waste, it leads to equipment damage, leads to lost production, as we saw in our 9E case study at the start of the presentation, and it leads to reduced efficiency. Inherently, these things are all not sustainable. So if we've got to rethink assets and we've got to stop looking at oils as consumables, well, we're going to need to rethink oil waste. We can't simply put an oil charge into service, watch it degrade, deal with the issues reactively that arise as they come, and then replace that oil. No, we need to start treating our oils like assets. And it turns out that oils are quite costly, both economically and environmentally. When you look into it, lubricant manufacturing is the most energy-intensive process in a crude oil refinery. For every liter of lube oil that is produced, 3.5 kilograms of CO2 will be emitted over the course of that oil's lifetime. So oils themselves are responsible for a significant portion of CO2 emissions. To see how big a problem this is, you need go no further than look at, for instance, how many lubricants or how many kilograms of lubricant were produced in any given year. In 2020, 37 billion kilograms of lubricants were produced. You do some very quick math on that. And in 2020 alone, the lubricants that were produced will be responsible for 152 billion kilograms of CO2 emission. Now, this strikes me as being a rather obvious place to start when it comes to making efforts towards improving our sustainability. So we got to rethink oil waste, because again, they're costly, not just economically, but environmentally. ASTM D4378 suggests to us that an average gas turbine oil really only lasts anywhere from 2 to 5 years. Now, if the turbine itself has a 25-year lifespan, that means that over the course of that turbine's life, we're going to fill it up at least 5 times with 5 fills of lube oil. Is that sustainable? Well, let's think about the fact that maintenance and sustainability, they are inherently linked by definition. So that means that if we do better maintenance, lubricant chemistry management, we can extend the oil's lifetime and we can reduce our impact. So case study here, rethinking how we do oil maintenance. Let's no longer be reactive and solve problems after they occur. Let's prevent them or be proactive in our maintenance programs. This particular end user went beyond business as usual. This is a new compressor driver, and that first charge of oil that was installed in that system, not only did they make sure that they had good filtration and water removal to make sure that the oil stayed clean and dry, they also made sure that they were managing their lubricant chemistry, and they did this by using ICB ion exchange resins from the very first day that that oil went into service. And you can see from the case study the MPC varnish potentials over time here. They stay nice and low, and the reason that they stay below 10, and often far below 10, is that those ICB ion exchange resins are removing oil breakdown products as they form. This oil is still degrading like any other, but you're actually managing that breakdown by removing the varnish-forming breakdown products on a continuous basis. The end result of this case study is really quite remarkable. This oil is in like-new condition after 13 years of baseload operation. And when you do a bit of a deeper dive into the lubricant chemistry here, and you look at some other oil analysis properties to project out the oil's probable lifetime, you'll see that this oil is probably going to last for longer than the equipment that it is installed in. So we have created a situation here where the oil's lifetime can match that of the equipment. We don't have to be replacing this oil and treating it like a consumable. So this makes us start to question current oil management practices again. Why are we throwing out oils after 5 years, for instance? So I thought I'd put this slide together just to show the costs, both economically and environmentally, that are associated with that business as usual approach. So for the purpose of example here, we're going to talk about a Frame 7F turbine. It's got a relatively large 23,000 liter reservoir. I apologize for not having that in gallons for anyone south of the border. Divide by 3.78 if you want that value in gallons. If we're not managing our lubricant chemistry in this system, well, again, if the turbine's going to last 25 years and you're replacing the oil every 5 years, that's 5 fills of oil for that system. So it's pretty easy to do some math and to figure out how many liters of oil you'll require and what the cost of that is. Taking a look at the carbon footprint associated with each liter of lube oil, you can do some more math. And you see that, over the lifetime of this turbine, the lube oil that is present in it is going to be responsible for nearly 400,000 kilograms of CO2 emissions. What if we do things a better way? What if we manage our lubricant chemistry, we install an ICB ion exchange resin from day one so that we are never allowing the oil to break down and varnish to form? Well, again, in this instance, we get a potential fill for life scenario where one need only fill up that turbine at the start and not need to refill it 5 times over its lifetime. And obviously, when you do this, you're going to need 5 times less oil. That oil is going to cost 5 times less. And it's also going to reduce emissions by that factor, by 80%. Okay, so now that we've gone over rethink in a fair bit of detail, let's move on to our second R. Because one of the ways that we rethought things was by removing oil breakdown products, not just treating them as an inevitability that, is to be tolerated and to essentially be disposed of once the oil is saturated with them. Oils are condemned as the result of chemical breakdown. I've said it many times before. The accumulation of varnish, acids, etc. This is why we are currently mismanaging our oils. So we need to manage these things if we want to manage the oils better. And the way to do this is by removing these using ion exchange resins like ICB. And this is how you treat an asset. So a case study, the best case scenario, the better way of doing things is to, use these ion exchange resins proactively to get out in front of the problem to prevent it from ever happening. But there is still a place for reactive maintenance because not everyone has, a turbine that has just been installed or a compressor that's just been installed and has a fresh charge of oil in it. Many people aren't starting from day one. Many people are like this case study where a power turbine had a fluid with a high varnish potential in it, and it was failing. It was experiencing valve sticking. Fortunately, it's never too late to remove oil breakdown products from your fluid. When they installed ICB ion exchange resins in this system, you can see a dramatic improvement over the course of 3 to 6 months. The MPC varnish potential of the fluid improved by 94%. From a reliability standpoint, very important, this power turbine hasn't had valve sticking issues yet. It has performed reliably. So the problem has been solved. Historically, this has often been an afterthought, this last bullet point, but in terms of sustainability, it may be one of the more important ones, actually. This oil charge was salvaged. This oil, which might otherwise have had to be disposed of, and when we say disposed, we likely mean incinerate it straight up into the air into CO2. This oil charge was salvaged. It's still in service in the turbine, and it's in better condition than it was when we started. So when we remove oil breakdown products, this brings us to our last R. We can restore a variety of things, not the least of which is reliability. A year or two ago, we had the opportunity to present at a large users group of gas turbine users. And it was a fun online presentation where we had the opportunity to do some, poll questions online. So one of the things that we asked this users group was how many of them had lost production in the last year as a result of an oil-related problem. And 20% said they had, 1 in 5. Now that shows us that people are not managing their oil chemistry, but fortunately, if you do, you can restore reliability in your system. You can prevent this downtime. So we talked about a 7F turbine a couple slides ago. Let's just look at what that downtime costs. Economically, it's not cheap. That's a pretty big turbine. Estimated losses in terms of generating revenue, if that turbine's down for 24 hours, on the order of $164,000. The one thing that I've always found a little bit interesting about that number is that one 24-hour loss is actually greater than the lifetime cost associated with lubricant chemistry management, associated with good oil analysis, and with using ion exchange filters like ICB. So if you can prevent one single loss over the lifetime of the turbine, you have paid off your lubricant chemistry management program. Another issue with reliability-related failures. If a turbine trips, for instance, it needs to be started again, and startup emissions are greater than baseload emissions. So it is more efficient to be operating constantly rather than turbines up, turbines down, turbines up, turbines down. So this brings us to another thing that we can restore. We can restore efficiency by managing our lubricant chemistry. This case study involves a gas turbine, a relatively small one, a 6 megawatt system or so, that was running hot because varnish had deposited in the coolers. Why does varnish deposit in the coolers? It's a shapeshifter. It might have been dissolved under operating conditions at operating temperature elsewhere in the turbine, but when it got to the coolers and was cooled down, it played it out and deposited it there. As a result, the coolers weren't getting the required delta T as the oil passed through them, and the high temperature alarm on the system started going off. Now, the engineers on site had a bit of a creative solution to this problem. They found that if they derated the turbine by 40%, they could keep the high temperature alarm from ringing off. Now, that is one way of doing things, but it's not necessarily the most efficient way of doing things because even on a small turbine like this 6 megawatt system, you do the math, and derating by 40% ends up costing about $350,000 in terms of annual loss. Perhaps more importantly than the economics of this, we know from the Siemens Westinghouse plot on the right-hand side of this slide that gas turbines operate most efficiently at base load. When they derated this turbine by 40%, that resulted in a 12% operating loss. Essentially, that means that they were generating less power per amount of fuel that they were burning. That is obviously not sustainable. Now, fortunately, again, this is something that you can react to. Would have been better to prevent or be proactive about this, But you can manage your lubricant chemistry reactively in many cases, and that's exactly what they did by installing an ICB ion exchange resin. Just like we saw in the previous case study, MPC varnish potential essentially plummets over the course of the next 3 to 6 months. And as that varnish is removed from the fluid, it is also removed from the cooler surfaces, and that allowed the oil temperature to come down to the point where they were able to return this unit to operation at full design capacity. Again, the last bullet point, one that has historically just kind of, been treated as unimportant because we've looked at oils as consumables, but they're not. This oil charge was salvaged, so this asset was saved. We can restore profitability. This is one that, obviously people like to see. One of the benefits of lubricant chemistry management is this potential not just to save on the number of reservoir fills that you will need, but also to save in terms of reliability. You're not going to be going on the reactive maintenance roller coaster anymore where, the system goes down and you've got to get it back up. You're losing production while it is down. So for this slide, we just kind of broke this into 3 different turbines to show you that it doesn't really matter a small turbine, a medium turbine, or a large system. There are savings associated with each of these when you manage your lubricant chemistry in terms of the lifetime fill costs. The smaller turbine has a smaller reservoir, so you save less, but it's still a significant savings. And reliability, if you are able to prevent one 24-hour loss annually for the lifetime of that turbine, you can save a lot of money. For the largest turbine in particular, that 7F we've been talking about, it's over $4 million saved over the lifetime of a turbine just by preventing an avoidable loss every year. Dollars and cents are important, but again, in this day and age, sustainability might be the bigger consideration still. So what impact does lubricant chemistry management have on emissions? Well, again, for our small, medium, and large turbine systems here, you can see that each and every one of them saves a significant amount of CO2 emissions from being produced as a result of more effectively managing the assets that are our lubricants. And again, the bigger the turbine, the bigger the impact of this change. So that's 7F. If we manage lubricant chemistry from day one, we can save potentially almost 320,000 kilograms of CO2 from going up into the air. And that brings me back to the slide that I started this presentation with. At the start of the presentation, I called this a better way, because I really do believe that this proactive way of doing things, lubricant chemistry management, is a better way. Here I'm going to call it making an impact, because again, this shows the opportunity to make a relatively small change. Manage our lubricant chemistry, run 1 extra test in your oil analysis, have a soluble varnish removal kidney loop filter skid installed on your system from day one, or retrofit some of your existing filters with ion exchange ICB filters. These relatively small changes, when implemented on a large scale, can have a huge impact, just like they did for this pipeline operator. And with all that, I'll just wrap up with a brief summary. So we've got kind of the take-home messages. If you remember nothing else from today's presentation, I'd urge you to remember that business as usual in terms of oil maintenance is not good enough. It's really important to be keeping our oils clean and dry, but this isn't the basis upon which oils are condemned. Oils are condemned on the basis of chemical breakdown, and we need to actually address this chemical breakdown if we want to operate sustainably and to truly manage our lubricant chemistry. Now, in this regard, varnish and related failures, the title of this presentation was eliminating these failures. Well, these failures result when oil breakdown is not managed, and this oil breakdown is a chemistry problem. So if you have a chemistry problem, you need a chemistry solution to solve that. Lubricant chemistry management, we believe, is the better way to do this, the better way to maintain our critical industrial oils. So what are the 2 pillars of lubricant chemistry management? Well, you need good oil analysis. You are blind to your oil's chemistry if you're not running a good oil analysis program. Make sure that you are obtaining complete and reliable oil analysis data. When it comes to your varnish testing, make sure that you are running the right test the right way and that you are acting on the results, and that you're running that test often enough that you can see problems as they potentially arise. In terms of the second pillar of lubricant chemistry management, you actually have to remove the oil breakdown products that are responsible for so many of the problems that we've talked about today. Preferably, you remove these as they form. You're proactive or preventative in terms of your maintenance. And when you do this, you can prevent accumulation of varnish within your fluid. You prevent accumulation, you prevent saturation, and ultimately this addresses the root cause of oil and equipment failures. Finally, all of this allows you to operate more reliably, more profitably, and more sustainably. And this is why we truly believe that this is a better way of doing things. At the end of the day, we believe, a little bit of math down here at the bottom, 2 pillars of lubricant chemistry management and the 3 R's of chemistry management really does provide you with this better way of maintaining your critical equipment. With all that, I'd just like to thank everyone for sticking around for almost the full hour here. I always started the presentation there with that picture of the mountains in the background behind Calgary. So I thought I'd jump away from varnish for 1 sec, show a picture of the mountains a little closer up. The Canadian Rockies are really awesome, so encourage anyone that's thinking about visiting to do so. And if you are visiting them, we would love to see you at EPT Clean Oil as well, show you around our Fluid Technical Center and talk lubricant chemistry management with you. And with that, I'd be happy to take any questions that we have time for.
Great, Matt. Thanks so much for the presentation. We've got quite a range of questions that came in during, and we'll just start in one from Peter. How does EPT view the problem of using varnish potential test as an indicator of breakdown for lubricants where the manufacturer has published information stating their lubricant is incompatible with the solvent used in the MPC test?
Yeah, we have questions about those claims from those oil suppliers. We ourselves have run the MPC test the way it's supposed to be run on those specific fluids. And when those fluids are in a virgin condition, when those fluids are in relatively good condition, we don't see issues with the MPC test, just like we don't see issues with conventional turbine oil that's new. When those oils have degraded, when we see high acid numbers and things like that creeping up, then we start to see varnish issues in there. I'm aware of one lube supplier that has mentioned that maybe the test should be run with isopropyl alcohol. My belief is that that actually just tricks the test. The test method, the way it is, it gives you a very good gauge on the oil breakdown that is in your fluid. And if people feel the need to start playing around with the test, that's probably suggesting that their oils are breaking down a little bit more than they would like to let on.
Great, thanks. Is varnish MPC value directly related to the acid number,
No,
TAN?
no, it is not directly related. There is a correlation in some cases, but I've seen many current formulations, more current formulations where a group 3 product is used, for instance, where the oil really doesn't form very much varnish, but its varnish potential can still become very high. I mean, one of the things that we've done here to try to understand at EPT Clean Oil how varnish forms is we've taken every major commercially available turbine oil on the market and we've subjected it to breakdown on our breakdown stand and tested it out the wazoo. And with some of the better products, we see that they do eventually form varnish, but that acids really don't accumulate in these systems. So testing for acid number on its own is not good enough in terms of qualifying your oil's breakdown levels anymore, because so many of the new products aren't prone to forming acids like older Group 1 oils may have been.
Okay, thanks. Turbine users consider the RPVOT test very important. Can you explain why, and is this a suitable test for routine condition monitoring?
I love the RPVOT test for a lot of things. The one thing I don't like it for is it is very costly, and as a result, it's a bit of a deterrent for running it. The RPVOT test, in my opinion, is the best test for looking at how much lifetime your oil has left. And that's a big part of lubricant chemistry management that we didn't have a chance to touch on today because of time. Other tests include things like LSV or ruler testing, so you can look at antioxidant levels that way. I like the RPVOT test because it gives you a direct experimental measure of how much oxidative resistance your oil has left. But on its own, an RPVOT test isn't enough to give you that picture of your lubricant's chemistry. It tells you how much more oxidation your oil can take, but it doesn't necessarily tell you how much oxidation it's already undergone and what your fluid's current propensity towards forming harmful varnish is. So I think regular RPVOT testing is very useful, but it doesn't get you out of needing to run the MPC test to check on varnish levels as well.
Okay, and regarding the third-party oil analysis reports, should we expect to see a range of hold times reported, not exactly just 72 hours that you mentioned?
Yep, no, good question. And yes, you should. It's 72 hours plus or minus 4 hours. So anywhere between 68 hours and 76 hours would be compliant with the D7843 method. So yeah, if your lab's reporting 68 hours, I'd suggest that they are way ahead of the curve because again, so many of the oil analysis reports that cross my desk have a delta E value and no hold time associated with it. You're allowed plus or minus 4 hours.
Okay, how do you regenerate saturated ion exchange resin?
It is possible to regenerate the ion exchange resins. However, the process when it comes to doing so tends to be more energy intensive than it is worth. As a result, these ion exchange resins are currently treated as consumables. And I acknowledge that that sounds like a less than sustainable approach. This is somewhere where we can move forward and we can do better. But for the time being, we have done our sustainability ROI calculations on this. And because you're using so little ion exchange resin, you may be using 2 to 6 kilograms of ion exchange resin to filter a 23,000 liter system. So the amount of ion exchange resin that you burn through in the lifetime of that oil, if you're replacing filters annually, for instance, the CO2 from that resin really amounts to a drop in the bucket compared to the oil itself. So it is still much better to be treating that ion exchange resin as a consumable than not to be managing lubricant chemistry at all.
Okay, does EPT provide an ion exchange filtration solution?
EPT provides a number of them depending on your specific application. We have our SVR, soluble varnish removal filter skids, so you can do kidney loop filtration of your system if you don't have, the possibility of an OEM retrofit. We have ICB FRF is our product for phosphate ester fluids, fire-resistant fluids. ICB RO is for our R&O oils that are used in turbines and compressors. ICB AW for hydraulic systems that aren't phosphate ester based, and ICB Jet for jet lubes. So these different ICB resins have all been specifically engineered and tailored to those applications.
All right, we've got time for just like two more quick questions here. Really, thanks so much for participating and sending these in. So what happens with the additives on AW lubricant if we use ICB media?
Yeah,
Will we have to refill with new oil, and what percentage?
I just mentioned that we have, a product specifically tailored for these AW oils. That product ICB AW, it has been engineered so that it doesn't impact the AW additive levels in those systems. We are nevertheless actually advocates for periodic oil top up. We think it is a good idea to maintain additive levels over time. And ICB ion exchange resins, they don't remove additives, but they also don't increase their levels. So as those additives naturally deplete over time, we believe that in most instances, a 5% annual top-up or bleed and feed is a very useful exercise in terms of keeping the oil healthy with its additive levels.
Okay, and one final one for you, Matt. And if we didn't get to any other questions today, I'll send them over to Matt and the EPT team, and they'll answer them via email for sure. Once varnish is down to an acceptable level, say less than 15, how long does it take for varnish to return when your equipment is running base load?
That really is different for every specific system, but just a couple of points there. I mean, it would depend on the duty cycle of your system. A harsher application, hotter fluid, hotter operating temperature, you're going to break things down faster. I noticed, you said varnish to an acceptable level, like less than 15. Less than 15 has kind of been thrown around as a target. I think ASTM even puts less than 20. But the closer to zero you can get it, the better, because I've seen a number of end users who have an MPC of 9 and are having varnish problems. So it's a little bit different in every application. And the way that you can most effectively mitigate your risk is by keeping it closer to zero. The other point to discuss based on that question is, just because you install a soluble varnish removal system and you get it from 40, for instance, down to 12, doesn't mean it's time to take that off. You can probably reduce your frequency of your filter changes on it because you're not cleaning it up anymore. You're in maintenance mode now. But we are big advocates for being proactive with these and actually keeping them installed on a full-time basis so that once you've cleaned up the oil, you're removing oil breakdown products as they form and you're preventing varnish going forward. And I see Scott has just copied and pasted my contact info into the chat. Its email is also up on the slide that's being shared right now. So I'd really encourage anyone that has any other questions from today. I'd love to hear from you.
Yeah, thanks, Matt. Sorry, I was talking while I was on mute. But yeah, thanks again for joining us today. And there were some other questions in the chat that definitely need a very in-depth answer to. So I'm going to send those over to Matt, and he'll be sure to respond to you. We'll have the recording available for you in a couple days. And just keep engaged with Combined Cycle Journal and EPT Clean Oil, and we'll see you for the next webinar. Thanks a lot.
Thank you.